Let's talk about the cross-Claisen condensations. Alright, so these reactions pretty much, just like cross-aldol reactions, are reactions between two different types of esters. And the best way to do this is to utilize an ester that doesn't have any alpha hydrogens, basically have it as your electrophile, and have one that does have alpha hydrogens so that you can make your enolate. So the best way for this one will be to first prepare the enolate to completion at negative 78 degrees Celsius temperature, and then add your next ester and let it warm up to get to the condensation product. So we kind of talked about this type of technique already. So the reaction will definitely go pretty smoothly. Now, as far as the procedure, well, first you would enolize your ester. If you do this at low temperature with a strong base, bulky base, you can ensure the deprotonation of that alpha hydrogen without undergoing any transformation from ester to amide, right? Because you want to prevent that from happening, right? So this base has to be at least somewhat bulky. But the deprotonation will happen. You will remove those electrons to form an alkene here and generate, in essence, your enolate, right? So we'll have a lithium enolate in this case. We'll end up, of course, with the protonated version of the amide. And once you fully form that ester, then you can add the other ester that you're trying to react it with, right? So the electrons can come back down from your enolate. The pi electrons will move over to attack the carbonyl carbon of the second ester, and those electrons will move over to produce an alkoxy group, right? And then at this point, you undergo the elimination because the alkoxy group will have its electrons come back down to reform the double bond, and at the same time it will kick away the alkoxy group that's present in that same position. So you end up with your beta keto ester product. And depending on what you're trying to do, you might want to do extra things here, but the last event, right, the one that drives the reaction also to completion, is the fact that the moment you form this beta keto ester, you have formed a very acidic alpha proton. So the alkoxy that you have around is simply going to deprotonate that alpha position, forming the enolate. All right, so here you can quench the reaction with water. You could even add alkyl halides to alkylate the product. It's technically up to you as to what you want to do with it. But for this purpose, I'm just going to go with the quenching in acidic water. So the enolate will attack the proton from your acid. You will then get the neutral product, and under the acidic workup, you'll be able to collect this in the organic layer. And once again, we are forming a beta keto ester, but this one is made from different types of esters, right? So you kind of have to play with this in a sequential manner. You cannot add the two esters at the same time necessarily and have the reaction go very cleanly, because the ester itself can attack another component of the same type of ester as opposed to the second, the benzyl, well, not benzaldehyde, right, but the benzyl derivative right here, the phenyl derivative. This, on the other hand, right, starting by first deprotonating your, let's go back here, deprotonating your ester with the strong base at low temperature ensures that you fully deprotonate all of the ester present in there. Mind you, you have to do it the way I described before, right? You have the solution of your base present in an inert solvent. You cool that down to negative 38 degrees Celsius, and you add slowly but surely that ester into the lithium amide solution. And once that happens, then you introduce your other ester. So it just takes patience, but the procedure is the same as described not only in this lecture, but also in the previous lecture. All right, so with that said, let's talk about this other reaction, which is technically a derivative of a Claisen condensation. This is called the Dieckmann reaction because the individual who, pondered about it was Walter Dieckmann, also a fella from the olden times, right? He was a golden boy. So what he basically did is he said, well, what happens if we try to do this type of Claisen condensation, but instead of doing it with two separate ester molecules, what if we take a big molecule that happens to contain two ester moieties within itself? So for instance, if we start with this molecule, this diester molecule that has 1, 2, 3, 4, 5, 6 carbons, in between the two esters, well, technically 4 carbons in between them. If you treat that with lithium methoxide or sodium methoxide, right? We're using methoxide because the esters themselves have methoxide. You deprotonate one of the alpha hydrogens from the two esters, and you generate the enolate of that component. Now, this molecule can attack another ester, but the fact that a second ester moiety is present in the same molecule means that this just be a rotation. Like if you look at this molecule and you rotate about this bond and you rotate about that other second single bond, you'll end up basically kind of rearranging the molecule. And you gotta keep in mind that at normal temperatures the molecules are fully rotating, they're fully translating. uh, the, these things are not restricted at all, unless there's a lot of bulkiness in the molecule. But the fact that this thing can kind of rearrange itself in space to kind of have this type of shape means that this enolate is gonna much more easily encounter the ester that's within the same molecule than to encounter an ester from a different molecule. So once this happens, we will have attack onto the second ester, and basically it'll happen as follows, right? And notice that here I'm kind of labeling things a little bit, but let me show you this properly so that you see exactly how that plays out. The labeling occurs from the ester now that I'm about to attack, the carbonyl carbon of that ester, and I'm making my way all the way to the alpha carbon of the enolate. This is going to play a big role because what this is letting me know, starting from the carbonyl carbon that I'm about to attack and ending at the alpha carbon of the enolate, it tells me how big a ring I'm going to be forming. Specifically, when this enolate comes back down to reform the double bond, this pi bond is going to attack that carbon and it's going to form a ring, right? Obviously, this will also form an oxo group. But the ring that we're forming is dictated by basically the numbers that we just determined right here, 5 carbons in total. And then we do the same thing we did in the past. We simply say, what do we have at the different positions? And if we start at position 1, well, at position 1, we're going to form this oxo, right, a lithium oxo component. But at position 5, we also have the methoxy component, right? So that's still going to be there. Then we make a way all the way to position 3, where we have a methyl group. So position 3, we have a methyl group. At position 4, where we have a methyl group, we gotta have also methyl group. At position 5, we're going to end up ultimately with the ester that we have regenerated in that process, right? And all of these components will basically then proceed to undergo the elimination, right? We have the alkoxy next to an oxo, so those electrons will come back down to reform the double bond, and this will kick out your methoxy group, right? Forming your beta keto ester. It happens to be a cyclic, but it's still a beta keto ester. And the thing to highlight right here is that this type of intramolecular cyclization, which is a Claisen condensation, technically speaking, is best approached when the rings you're forming are 6-member rings or 5-member rings. They have the best bond angles, the least amount of strain, so it works great when you're forming those type of rings. However, if the ring size that you were to be forming would differ from 6-member rings or 5-member rings, if they were smaller, like the ones here, or if they were larger, like the one I'm showing right there, then you probably will not end up forming that intramolecular cyclized product. So basically stick to 5 and 6-member rings. And you might say, okay, well, fine. I mean, that's just going to come from me because I'm the one designing the problems. But but let's say that you have a situation where there's actually more than just 2 esters. Well, then now there's multiple things that you have to consider. Because if, let's say, we start with the ester here on the far right end of the molecule, well, starting from that ester and going to the nearest alpha carbon of the the subsequent ester, the second ester in the molecule, you will count a total of 9 carbons in this sequence from left to right, or technically I guess right to left. And what that will mean is that, well, if these things were to cyclize, you will form a ring that is much, much bigger than a 6-member ring. So that's going to be a no-go. So if instead if we, at position 7, we make our way to the other ester, well, that will still give us a ring that contains 8 carbons in the sequence, and that's still too big of a ring. So that will tell you, okay, so the ester at the end is probably not going to get involved in the cyclization reaction. Okay, but on the other hand, if we consider, let's say, the ester down here, call that position 1, and we make our way to the nearest alpha carbon of the second ester, which will be the one over in this position, that will give us 5 carbons. And so that's good. 5 carbons, 6 carbons, that's good. So we can form a ring with that molecule, right? So we have the 5 carbons, and just as label, at position 1, we're going to end up forming the lithium oxo, right? Because that's where the attack is going to happen. At position 1, we'll also have the methoxy group. Positions 2 and 3 are free, there's nothing there. At position 4, we're going to have this long chain, which has 1, 2, 3, 4, 5 carbons, and then the ester. So we'll have that whole thing, 1, 2, 3, 4, 5 carbons, and then the ester. And then at position 5, we have the remaining ester molecule, right, that was there to begin with. And just to be on the same page, position 5 is the position where the deprotonation happens. That's where the enolate gets formed, and that's the enolate that attacks position 1 in the ester down here. All right, but there's going to be one more thing that we have to account for, right? So that lithium oxo and methoxy will do one more extra thing. The methoxy group will be kicked out, and you will form that double bond. So you end up with that final product at the end of the process. But the extra thing that you have to consider is what happens if instead you deprotonate the alpha carbon here and you attack the carbonyl carbon of the ester up there, because that will still be 5 carbons in total. And if we go with that premise, well, at position 1, we will have lithium oxo and we'll have the methoxy group. Position 3, we'll have the long chain leading to the ester, right? And then at position 5, we'll have that ester sticking out. And you might say at first, okay, fine, the methoxy group's going to take off, form that double bond. You might say, okay, well, that looks pretty much the same as what we drew before. But if you compare them side to side, or technically top to bottom, what you're going to see is that actually they are different molecules, because it's, if you keep the numbering the same, right, from carbonyl to alpha carbon, at position 4 is where you have the long chain appearing, whereas on this other situation, the long chain appears at position 3 as you go from ketone carbonyl to alpha carbon. So they are in fact different molecules, and in some situations this is going to happen, in other ones it will not. But you have to be aware that yes, you should be checking both sides to make sure that things may work out. Another thing that you could also check is that when you look at this molecule, the common ground you could say is position 3, right? If you come from position 3, you have 1, 2 carbons before you hit this ester, whereas if you go from the top portion, you only hit 1 carbon before you get to the ester. So you have basically 2 different types of esters, and that's what leads to the asymmetry. In other situations, you'll have the same amount of linkers, so you'll end up with the same product regardless of which one is the enolate and which one is the ester that gets attacked. Okay? So with that said, in the next video, we're going to talk about how else do we go about preparing these diketo, beta diketo compounds. And then we'll talk about how we can use them for synthetic, purposes. So catch you in the next video. Bye-bye.